Thank you, Anna. That is a great introduction. That through this whole adventure, Anna has been around through most of it. In fact, one of the first nights I went to a telescope, Anna was there, the 4-meter, measuring star streams, and it's been a pleasure to go on a journey with her. But yeah, thank you so much for having me. I'm so excited to be here, and yeah, talk to you about the first first Galaxies at JWST. Before we get started, I'll use this figure to really situate us in this talk as we go on this journey, very early epochs. It's one of my favorite figures in all of astronomy. It's back in the day when we still had interests that were situated in the distant universe. And I like it because in a few pixels, it really contains our cosmos tree, right? So we're starting off with the Big Bang over here. The cosmic microwave background is this greenish hue, following which the universe is this cold, dark ocean of neutral hydrogen. There's no stars and galaxies yet. From that, the first stars begin to emerge, the first galaxies emerge, and one of the first things they do is they blow these ionized bubbles around themselves. These are the first ionized region in the universe. These bubbles coalesce, overlap. This is what we call the epoch of reionization. And then finally here, we're sitting in a galaxy like this today, trying to make sense of everything that has come for us. The story that I've just told you, for the most part, is still very much a story. It's in this whole image in these billion years. There's only a handful of galaxies that we really understand with spectra, with detailed information. And so that is exactly what is changing right now. That is the revolution we're in the midst of. In this talk, I'll touch mostly on 2 topics. I'll address questions about the very first galaxies, when were they born, what are their properties like, what are we learning already in the first few months of JWST. And in the second half, touch on what are the outstanding questions, how they reionized the universe, how did they drive these bubbles, what is the nature of that particular epoch in our history. One thing I find pretty profound, this might be a hat to most of the people in this crowd, but I really enjoy the idea that we can directly observe this happening in real time. And so to use an analogy, imagine there was a window in this room, and because from Boston, and I'm going to use Boston-related allegory. And imagine you could stare really hard out of the window, right? And you could immediately directly see Tom Brady being divorced or retiring, but winning his first Super ring. If you looked out slightly further, you might see the Boston party happening live in action right. And even farther, you would see dinosaurs frolicking across the Boston Green or whichever part of the league. And this is something we do in galactic astronomy all the time, right? I mean, we might be a bit jaded and used to it, but we are really seeing galaxies as they were at these very early times in situ. And another way to think about this is when we look at these first galaxies. This is a cartoon I'm going to play from the national broadcaster in Japan, who clearly was very excited about educating the public about redshift and higher galaxies. This is clearly very important. Is that when we're receiving light from these distant objects, we really are beholding them as they were in their infancy. So those galaxies are evolving right now. They're going through college, middle age, retirement. We are still beholding them in their very infancy. So what we're seeing when we're seeing all these galaxies simultaneously in some of the deep Hubble field images, like the one that I opened this talk with, is we are awash from images of galaxies in their infancy, in their middle ages, across all these phases of life, right? But there's 2 effects that really help us identify these real babies, these real infant galaxies from these very early times. So here's a graphic that illustrates this. So what I'm going to show you here is a movie. These are Hubble Space Telescope filters that likely you are familiar with. We're going from the Hubble, so this is about the F435W corresponds to the visual wavelengths, all the way into the IR to about 1.6 micron. So that is Hubble's reach in terms of the kind of photometry it can do. And what I'm showing you here is the spectral energy distribution for a galaxy that I'm playing at redshift 3. Okay, And so in this movie, I'm going to show you what happens when we move this galaxy to higher and higher redshifts at fixed intrinsic luminosity. So what you see is that at very high redshifts, all the light from the galaxies is basically completely shifted into infrared, right? And there's two things going on. One is because expansion of the universe, all this light is shifted into the infrared. And two, because these galaxies are completely ensconced by these bubbles of hydrogen around them, this neutral hydrogen soaks up all blue photons in the spectra of these galaxies. So a very characteristic feature of these very distant galaxies is that they're detected only exclusively in the infrared and completely blotted out at these bluer wavelengths. And so with Hubble, already we pushed our array all the way to about a redshift of 11, close to 400 million years after the Big Bang. This was a study made by Pascal Ush in 2016. I was a young, impressionable undergraduate in the Yale Astronomy department when all this was happening. And perhaps it's no accident that I'm giving you this talk today, because this happened around me. And what we did back then with Hubble is really pushed it all the way as far as it go to about a redshift of 11-ish. This is a galaxy that's detected only in a handful of bands with Hubble. But you can already see that we were kind of already a limit of what we could do in terms of finding these very infant galaxies. And where JWST comes in. JWST picks up where Hubble left off and goes all the way with super sensitive photometry out to about 4.5 microns. So galaxies that appeared only as blobs in one-band detections, we now have multi-length photometry for them all the way out 4.5, 5 micron with very sensitive spatial resolution. And so this is a galaxy found within a few days after the first data release for JWST. It's a galaxy we call very creatively Z11, like G11. And here I'm showing you the spectral energy distribution of this system. So this again is a galaxy that is very well detected in all these infrared wavelengths, and then completely disappears in this blue band that we have extremely deep photometry in from Hubble. And so the redshift that we fit for this, based on where this galaxy disappears in these bands, is a redshift close to about 10.5 to 11. So already in the first few days of JWST, we were able to find a source that pretty much was a match to the best we got out of Hubble. So this is really interesting. And it's not alone. So we found another galaxy that is even slightly farther away based on photometry. We call them Galaxy 11, Galaxy 13. Appeared to be a few hundred mega years after the Big Bang. And so this is quite a spectacular surprise that I'll explain in detail as to it is such a spectacular surprise. But before that, I want to say it was a pretty wild experience that we made these images on our computer, and before we knew it, they were kind of like being printed all around the world by journalists who had been refreshing archive and who had written articles about these papers before we even finishing them to the journal, right? And the pinnacle of the whole experience of seeing these images go everywhere was when Chris Evans, Captain America himself, who everyone's a huge fan of space and space-related things, retweeted this to something like 100 million people. And before we knew it, we were getting newspaper cuttings. This is from one of my science teachers, my high school science teacher, who sent a picture of this from the Headline Times. That is a small city in India that I grew up in. I talked to them in maybe 10, 15 years, and they were like, hey, I just saw your name in the paper. So I see you did not end up becoming a computer science engineer at Google or something. That you're doing something funny with your life. But yeah, this was this initial really burst of results about Galaxy JWST. It was quite affirming to see that the general public and people in general cared about things that were not aliens or black holes, and that the things that we worked on really meant so much to the public, not just here in the US, but around the world. But yeah, after these initial discoveries, there's been a flurry of galaxy candidates at these very high redshifts, so greater than 10, at some of the farthest distances that we have potentially seen. And so here's a mini instrument for the annual review of astronomy and astrophysics. Here's Richard doing a mini review on Twitter, where he compiled all these candidates from all these various studies. One of the things was that these various studies were finding sources were kind of like, even though they're studying the same fields, we're not finding the same samples. There appeared to be like really a large number of sources that people were studying. But for the next few slides, I'll focus on why these particular bright galaxies are pushing our galaxy models and what I'd be teaching us about cosmology, about galaxy evolution. Again, we did expect JWST would find galaxies at these very early epochs at distances we'd never seen before. But what is particularly interesting are these bright sources that really appear in pretty much every single study that has tried to go looking for high redshifts. So here I'm showing why this has been such a spectacular prize. So this is a plot I'm showing you from Sandra's 2018 paper based on a model that we've worked on, which really reproduces pretty much every high shift observable, like the UV luminosity function and such, the pre-JWST era. And what we're projecting here is how many galaxies we expect at these kind of redshifts, redshift 10, from all the extremely deep JWST programs, pretty much at the end of cycle 1, right? And so the projection was that at the end of cycle 1, after surveying more than 10 times the survey area that we had seen from the early release science data, we would maybe find a handful of such galaxies. And we're already seeing these systems within a few weeks of the early release observations. Another way of looking at this is by looking at UV luminosity function. So here I'm plotting the number density of sources versus how bright they are, right? And so the idea here is that the implied number density of these sources is more than 10 times offset from a leading theoretical luminosity as well as extrapolations of what we see empirically at lower redshifts between 6 and 10. Another thing I'll highlight here is that the sources in purple perhaps are not necessarily as much surprised because in G11, the source I was showing you earlier that we found Hubble, was at an implied density much higher than pretty much any model suggested. What we are seeing is that this source is not just some isolated oddball, and there is genuinely something interesting happening at the bright of the luminosity function. Here's why it's interesting from the perspective of dark matter. So we have very successful set of models that have reproduced pretty much every observable in the first years that we have from grammetry in the last few years, where what we do is we say that take a dark matter simulation, a pure dark matter only simulation, and in each dark matter halo, you say that our formation rate is basically a function of the accretion of dark matter onto it. So the star formation rate is basically set by how dark matter you're accreting. Convert that into some kind of star formation based on efficiency that you calibrate at redshift 4 or so. So this model has pretty much like successfully explained things like this very rapid drop in the total overall integrated star formation density at early times, just in bright galaxies, which are a tiny fraction of whole integral, and a variety of other observables. But it turns out that this whole class of models really fails by in an order of magnitude to take the frequencies occurrence of these very bright galaxies. And so this is a problem that has been called the quote-unquote too big to be problem, where we are potentially seeing galaxies that are brighter and more massive to fit into these halos and dark matter halo from our simulations early. And of course, there is a problem with dark matter. There's going to be solutions, and so there are some of the solutions for too big to be. And this really has been quite quite an area of excitement and interest. And so my sampling of picture is going to be quite incomplete. But broadly, there's two classes of solutions people have come up with to address this occurrence of very bright galaxies. One class is to tweak with cosmology or dark matter, because that's very exciting. So people have things like invoking early dark energy, gives you more time by redshift 10 to form like more massive halos, because he'll grow at this pretty rapid. And so what early dark energy does is at redshift 10, the universe is not over 100 mega years old, but it's even older. So that gives you more time to grow these early galaxies. There's also been tweaks suggested dark matter itself, where you can make these halos very dense. They can hold on to gas better, have higher star formation tendencies. For example, people have proposed that primordial black holes end up producing this kind of like denser, clumpier dark matter. And the other class solution, I personally think, is where the answer lies. Every time there's a problem with dark matter, you always blame the baryons, and the baryons are often found responsible culprits for creating whatever problem you have at hand. And so there's plenty solutions here. So for example, maybe your IMF early times, your initial mass function is very different, very top heavy, where you have a lot of very massive stars, but no corresponding low masses, as we see in the Milky Way, because you never measure star masses, right? You always infer stellar masses, and that inference would be confused because the IMF is just off. I've also written about how POP3 stars, very metal poor stars, be much more luminous than we have in our models. There might be AGN information that we're seeing that are brightening these galaxies momentarily. Maybe the dust physics are very different, where these galaxies just do not have any channel dust at all, and so we really are seeing them shine so brightly. Another surprise is, so that's one too big to be. I'll do it in a second. Another set of surprises has been on the morphology of these galaxies. This is kind of like the most extreme example, where in Galaxy 11 we have some evidence based on modeling the surface brightness profile that it might have a fairly extended disky-like profile at red 11. This is analysis that was by Erica Nelson and Galaxies, who've also published papers arguing even at lower redshifts, between redshift 6 to 10, the frequency of disky-like is much higher than we previously expected, based on this initial morphology kind of analysis from images. Galaxy 11 is also interesting because when you look at Milky Way, we now have just very recently fully put together a pretty compelling picture when our own galaxy acquired a rotational component. This is a paper from earlier this year where we said seeing the birth of the galactic disk. And what you see here that very early on, the kinematics of our galaxy are very scattered. The stars do not have ordered motions. And then something happens between around redshift 4 and 6, and our galaxy begins acquiring a net rotational component, the birth of a high alpha disk. And what is very interesting here is that the stellar mass of Milky Way at the time when this rotational component is acquired is very similar to the stellar mass that we infer for Galaxy 11, which is times 10 power 9, which is perhaps something about the characteristic mass scale at which when galaxies are able to acquire this kind of component. We're still calling these galaxies redshift greater than 10 candidates, mainly for two reasons. The first one had to do with calibration uncertainties. So we were dealing with this new instrument with NIRCam. Calibration versions were still ongoing. But I'll just say that here I'm showing you CMDs of a globular cluster, the same globular cluster, where these CMDs are constructed based on the various chips in the detector. So these CMDs should not look different. You see, it's still the same globular cluster, no matter what chip of your detector it's on. So this is kind of like the state of calibration when many of these first papers were being written. So they're concerned that perhaps these calibrations are driving our inference of these studies. But I want to point out that since we've really like hammered this down, and now for the photometry, like we are doing precision percent level photometry with NIRCam at least, And this is no longer an issue for all the inferences I just described to you about these two objects. Another more trickier, also very exciting reason why we're calling them candidates is we are looking at the universe at these wavelengths with such sensitive geometry for the first time. And so there's entirely new classes, interloper galaxies, that could pretend and mimic the signatures of these very distant source sets that just do not exist in our models at all. And so here's what I wrote about one such galaxy, I think, that Schrodinger's galaxy, which all our models tell us very confidently is at redshift 17 based on its photogrammetry, unambiguously, and the latest zero corrections. Whatever model you throw at it, the answer is redshift 17. But I noticed that pretty much every galaxy in the field around it is at redshift 5. And if you fix your redshift to redshift 5 and then like go building custom models with like random emission line templating on an AGN and on very hot ionized gas, then able to build a model like this, where you have an extremely dusty starburst. So because of the dust, all your light is completely soaked up. It has to be very low mass, and it has to be a starburst because light is completely dominated by these very strong emission lines. And so what usually happens in dusty galaxies is you end up with kind of a red continuum. What you instead see here is this kind of like blue slope in the photometry because it's being fully driven by these emission lines. But again, we've never seen a galaxy like this. We've never seen so much dust, such a low mass galaxy, which would totally red mass metallicity sample. So there might be objects out there which are able to like mimic the signature of these very high redshift galaxies, and that we really need spectroscopy to confirm these systems. And so for a particular galaxy, we will have spectra in a week from now, I think. And so we'll very quickly collapse the wave function of this galaxy and the answer exactly at last.
Okay, so a few more questions on details about this. So I'm curious, how much would the mass change of these two sort of galaxies for everything to not be broken? I'm curious about that because there's still like in terms of the propagation on all of the H2s of web, as far as I'm aware, that hasn't been fixed. So I'm curious that like if the error bars alone be sufficient to sort of blame the or what these powder bars are calculated, maybe would be another question.
Yeah. No, that's exactly why I prefer to always couch this in terms of UV luminosities, because that is we're pretty much very close to directly seeing with minimum modeling. And so this part, like, we still need to explain it somehow, you see. So yeah, so the conversion to stellar mass and then like arguing about how you can fit those stellar mass halos, I think is a need. It suffers from all the systematic described, which is why I prefer to fit in terms of let us look at UV brightness. How do you make these things bright? Is like what their actual masses are. So that does remain up a little bit, whatever calibration, whatever is your point, whatever you throw at them. But yeah, you had another question, or? Yeah.
Okay. And then I'm curious on the Schrödinger galaxies, like what aspect of EV is sort of outside the, like when you run like a typical Odyssey model, why define this?
It's a combination of like the emission line ratios. Okay. The emission line ratios are not typical emission line ratios. And also, yeah, amount of dust at these low masses. If you have like some kind of VR that's baked into many of these models, then you really have like go pretty far off them there. Okay. So what we get for these objects is spectroscopy to answer specific kind of questions that have been raised. So there's two facilities that are capable of measuring stuff for these very high redshift galaxies. One is ALMA. So ALMA can pick up in principle far infrared features such as 0.338 micron emission, which at redshift 10 shifted into the ALMA bands that are really sensitive. The good news and the bad news for these objects is that you see nothing when you look at the source in ALMA with reasonably deep ALMA imaging. And so what this does, right? So good news is that a whole class of interlopers, like super dusty galaxies that I showed you, should be extremely well detected at ALMA wavelengths if that is indeed what is happening, because the light that is soaked up by the dust is re-radiated at far infrared. But then the bad news, of course, is you still do not see anything. We still do not have a redshift based on the emission lines for these galaxies, and that essentially implies that these systems are metal poor. And the upper limit on their metal is based on these non-detections are about 2% solar, which again, is perhaps what you'd expect for very early systems where you're barely even settling the type 1a delay in distribution. You can go to JWST for spectroscopy, where you pick basically the line break. And so what I'm here is a simple split based on simulations of prism observations, so very low resolution spectroscopy. And what you're looking for there is this very sharp break that is produced by complete absorption and a flux in the IGM, where all these other low redshift interlopers should have something more of like much smoother decay in the flux. And so you should be able to see this in order like 4 to 5-ish hours. With JWST. And so that is what's coming soon. And so in the next week or so, of these candidates are going to be observed with this mode. And so we have this kind of data to really deal about what's going on. I want to stress a bit now and talk about cosmic reionization, which is this question of how did these first galaxies reionize the universe? How did they have these balls that then coalesced and ushered us into this hot and ionized universe we now inhabit? The way folks typically think about reionization is in terms of some net number of ionizing photons we need to produce to keep all the gas in the IgM in an ionized state. And where your ionizing photons coming from? They're coming from star-forming galaxies. They're coming from star formation in galaxies. And so what you do is you take your number of galaxies, you try and figure out some sense for how many ionizing photons are being produced within each galaxy. And then you multiply by some factor where of these ionizing photons that are being produced, some fraction of them manage to avoid all the dust and neutral hydrogen within the galaxy and escape into the galactic medium to produce cosmic reionization. So that is roughly how we parameterize this and about this problem on a pretty large scale. And so we're going to be very good at counting galaxies via Luminosity. This is essentially what you get out of your Luminosity course. And we're also going to be good at measuring how many ionizing photons are being based on the strength of emission lines. And I'll show you in a second how we're going to do that. But the really tricky factor that's going to be very difficult to pin down is the escape fraction, the fraction of galaxies that evades dust and neutral hydrogen galaxies used to reionize the universe. And so here's how we're measuring psi-ion. Yeah? So this is a survey that we just finished taking half the data for about a week ago. So the survey we call the first reionization epoch survey that is complete, an acronym that actually makes sense. And so this is the kind of survey that's going to really pin down the ionizing property of these early galaxies. So what I'm showing you here is it's a GRISM program. What you get is for every single galaxy in the field of view, you get a spectrum, which is both, for every single galaxy field of view, you get a spectrum. That's super exciting. For every single field of view, you get a spectrum, which is also so very complex because all of them overlap with each other. But these kind of surveys, these kind of blind surveys, where you get all these diagnostics at these various redshifts, in particular, at redshift to 8, for the first time, you get Balmer lines, things like H alpha and H beta. You can directly constrain the ionizing photons at those epochs, the production of them. Here's what some of early results look like, where instead of showing your projection, I'm showing you stacked spectra And so we're going all the way from very low redshifts. We're seeing Paschen alpha. Paschen alpha is the most common line. So if you have any ideas about what Paschen alpha, we have tons and tons of Paschen alpha emitters. Currently, we've worked all the way to betting galaxies at about redshift 6, where we're seeing alpha, we're seeing all these other lines. And eventually we'll complete this all the way out to redshift 9. And so through these kind of studies, we are directly measuring the strength of ionizing photons and produced within these galaxies.
So remind me, the near-term prism is like R of 1,000-ish, so it's enough to actual and
yeah, it is. It's more. In fact, it's R of 1,500, which is that's right. Which is a huge step up from the JWST prism, right? Where people usually are used to thinking of R of 100 prism spectroscopy. So this is really quite high resolution. The way to look at it is NISPEC's medium resolution. What you get out of near-term prism spectroscopy. Yeah.
What fraction of their sources we also be getting decent measure of H beta to get the
yeah, that's exactly what I'm going to propose to do the other GRISM, so FP6W, because now we're basically getting H beta none of them. Yeah. But no, that's a very obvious thing to do. It'd be super exciting, right? Because then you'd make dust corrected star formation maps of galaxies at redshift 6, which would be very.
It seems like in every row there is like one line that is most done. So how confident are you that line opposite of age?
Yeah, no, that's indeed what we struggle a lot, right? But the thing helps us is we are doing this in fields that have the most exquisite photometry across the entire eye. So you have very strong constraints already for photometry of what you expect. So we joint model for you along with spectroscopy. So you convolve the metric redshift posteriors with the posteriors. Okay, doing this, and we're figuring out what the ionizing production is within galaxies. But the tricky thing still is the escape function, which has been this bogeyman that has haunted us for a long time. And really, everything hinges on Lyman continuum escape, right? So like this escape of ionizing photons. So I'm showing you two models really differ in their distribution of escape fractions, managed to match pretty much most of the other constraints in the literature. So here is a model where basically the faint galaxies, the very faint galaxies that we currently do not do any spectroscopy of in our surveys that are like 1% L star or lower. These are the galaxies that have high escape fractions, and then this very smooth kind of reionization in history, because these galaxies already place at very early times. But when you have more massive, when you have bright galaxies that have high escape fractions that are more ionizing, then you get very delayed, very rapid kind of reionization, which is what some of our latest measurements from Planck and from statistics of quasars and Lyman alpha emitters are suggesting that reionization is actually very late and very rapid. For that kind of reionization, galaxies having very high escape fractions, it produces this kind of very delayed reionization history that matches kind of constraints. And the key thing that's different in these models is really the escape fraction distribution. So this is something we want to constrain because it really has so many ripple effects for galaxy evolution across cosmic time. So what's at stake is what the reionization looks like. So if you have very biased state tracers, these very bright galaxies that are driving these first bubbles, the kind of topology of gas that you have is very different from when these much more distributed fainter sums that are very uniformly distributed are this kind of puckered history. And if you have things like quenching in ultra-faint galaxies, or how star formation is regulated in terms of the that's collapsing onto halos, the differences in these topologies have very wide-ranging rippling effects. The reason the Lyman continuum escape question has been so difficult is because for any individual galaxy at significant redshift, you can't ask the simple question of what are the properties of a galaxy with high escape fractions versus low escape fractions. And the idea here is, it's kind of like you're in a plane and you're looking down at some random city that you're passing over. And you want to tell how bright that city actually is. But there's some amount of fog that's enveloping city that you have no constraint on whatsoever. And so you can't quite tell how bright your city ever is. And that's been the fundamental impasse in this where you can't tell whether a city is shining bright because there's fog there today. Or the flip side, you can't tell, oh, the city is completely like dark and blocked out because maybe it's totally shrouded. And so to break through this fundamental impasse, one thing that we have proposed and that a lot of empirical evidence has forward is that instead of measuring these ionizing photons escaping from galaxies, which you can do about redshift 234, but beyond which it's completely impossible because all these the neutral gas around these is completely soaking up the photons. One thing you can do is you can get Lyman alpha instead. So what I'm showing here is a figure of how various types of photons being produced in a young galaxy are escaping out of it, right? So here you have UV photons at about 1500 angstrom that are kind of like streaming through all this neutral and dust that's distributed within the ISM of the galaxy. Attenuated for sure, but they're kind of streaming through. Ionizing photons are immediately soaked up by this neutral hydrogen and by all the dust. But Lyman alpha photons, on the other hand, take this very zigzag route, being absorbed and then being re-radiated and processed by the whole ISM, and then they emerge the galaxy. And the whole journey that they take is imprinted in this very detailed high-resolution line profile of Lyman alpha. I'll show you in a second how that works. The picture to keep in mind is that Lyman alpha photons really are like Odysseus, like Ulysses in the Odyssey. One of my favorite maps summarizing a novel. So the Odyssey is about Ulysses trying home from Troy. So he starts from here, right here. But the journey that he takes is you see across this entire map, and he finally ends up in Ithaca. But the idea here that Lyman alpha is taking this whole journey through the galaxy and then coming out and emerging with tales to tell about what really lies inside in terms of the gas and dust geometry distribution. And so what we've seen, the argument made is that when you look at these Lyman alpha belts that have extremely tight peaks, that is a strong signature that galaxies are really leaking ionizing photons. Lyman alpha hasn't had a difficult time emerging from the galaxy. There's a lot of flux close to the line center. Versus here, the Lyman alpha has really struggled a lot. Rings are very broad. The distance between these peaks is very wide. It's been a much difficult journey. And so if Lyman alpha struggles so much, then continuum is totally dead already. Another way of looking at this is by quantifying what fraction of Lyman alpha is escaping close to the line center. In galaxies where it's very low, this is a strong signal that photons are just rushing out. And so we operationalized this idea, this survey that we undertook over the last 2 years using the X-shooter instrument on the VLT, with really exquisite resolution. And we targeted a sample that's very well defined. It's a flux limited Lyman alpha sample. You have coverage all the way from Lyman alpha to H alpha. And put together this idea of how exactly ionizing photons escape from galaxies. And so this is based on analyzing all the various features from Lyman alpha to H alpha simultaneously, where we have this picture where initially stars are born with these very dense clouds. No photon escape because they're still in this very dense state. Then for a very brief period, only less than 10-ish megayears, you have this period of very high escape fraction, photons really oozing out of galaxies. But then the vast majority of your galaxies, at say redshift 2 or 3, are actually in this phase in 4, where they still are UV bright, right? Where they still are Lyman alpha emitting, but they're not connecting to the ionizing background. So like one key idea that emerges from these constraints is that it is a very small minority of galaxies at, say, redshift 2, we did all these measurements, that are contributing to the overall ionizing ground of the whole universe. So for example, alpha emitters are only about 10 to 15% of starring galaxies at redshift 2. And all 10 to 15%, only half of them are in this phase. So it's a very oligarchic distribution of where your ionizing photons really are coming from. And what you can do is you can take these insights and really forward model the whole cosmic ionizing background and answer some questions that have really remained open for a long time. For example, one key like enigma in this field has been why is the ionizing background so flat across a wide range of cosmic time, right? If you look at the star formation density of the universe, it's changing by more than an order of magnitude between these redshifts. But if you look at the ionizing background, which is shown in gray here, it remains flat. And so how do you explain that? And so it turns out that with this framework we've developed using Lyman alpha, you get this quite naturally, because your UV photons are disappearing with time. So these are photons being produced at about 1500 angstroms. Measure your star formation density based on that. Based on these stars that are 50-ish years old, they are declining with time. But your Lyman alpha emitters, or stars that are in these very young galaxies in these very metal poor environments, their relative function of the whole star formation density is going up. And so those effects really balance themselves out and really give you a very flat ionizing background across time. So what we do with JWST is apply these insights to really try and understand what is going on with escape photons really in the heart of reionization at these very high redshifts. So one such experiment that we designed that we're going to execute with JWST within the next few weeks. So we've been scheduled for around Christmas. So it's going to be a pretty fun Christmas where we deal with GRISM data instead of presents under the Christmas tree. And so what I'm here is we're really zooming in, performing a survey on one big ionized bubble in the epoch of reionizing. What is going on in this bubble is there is one Lyman alpha emitter, white galaxy that we know of, that has the Lyman alpha profile. And because you all are experts in Lyman alpha profiles now, you see that these two peaks are quite narrow. And this is probably a galaxy that is leaking ionizing photons. But what is also very interesting is we see exactly where this profile cuts off. So showing you in red is kind of like a very well-matched profile from a redshift 2 galaxy in a universe which is sitting in a universe that is quite that is not being processed by neutral hydrogen. And what you see based on this comparison is just like a quick cutoff somewhere on the blue side, and that cutoff basically corresponds to what the edge of this bubble is. And so what we're learning from this profile, there's a galaxy that is contributing some ionizing photons, but it's also sitting in this much larger bubble whose size we now know. And if you know the size, you know what the total ionizing budget within that bubble should be. Kind of like analogous to a Stromgren sphere, where the amount of your ionized, the size of your ionized region translates to what ionizing power is. And so then we can perform this very controlled experiment where we can go and really see whether the other galaxies within this ionized region, there's bright galaxies with very high ionizing photon production that are powering this bubble. We see that these bright galaxies are just not able to sustain the level of ionization need to drive this large-scale bubble. That would imply that there's much fainter systems that are far below our detection limits that are doing all the work. So this kind of control experiment is something I expect we'll be able to do on a much larger scale, many other systems in the coming years, as we have instruments such as MIRMOS, for example, that's being done here by many of you in the audience. We'll be able to do this kind of Lyman alpha spectroscopy from ground and then go do these surveys with the JWST in these special regions where we have constraints on the geometry based on the Lebanov. I think I'll end here. Here's a summary of a talk that I did not give today, which is as Anna was introducing, Milky Way's farthest regions, about the Milky Way stellar halo. Very happy to talk about this topic. If you want to sign up, there's I think still a few slots on my schedule. Happy to talk about dwarf galaxies we've discovered, their data, what we're doing next, the kind of surveys we're going to plan to like extend that map I've made there all the way out to 100 C and beyond. But yeah, this is the summary for this talk, and I'm kind of happy to take questions.
Thanks, Rohan. There's a quick announcement. I'm not sure actually there are slots, so I'm pretty popular, but there are spots for dinner. If you want to join for dinner, yeah, please let me know. So that questions.
Thanks, Rohan, for a very interesting talk. So when you're showing these double horned profiles, and measuring bubble sizes based off of them, I'm curious if you can talk a little bit about sort of constraint you get on the size from that and what goes into the model, because as you know, degeneracies, dust, and geometry sort of cause issues with making very direct differences. And so I'm kind of curious how you did the modeling for this, or if it's mostly, yeah, basically, if you can talk a little bit more about how you did the modeling, that would be helpful.
Yeah, there's various levels of complexity you can apply modeling, right? So like most basic thing you can do is kind of like think of like a quasar proximity zone, where you have some distance that you can compute, assuming that this is the systemic redshift. Yeah, what's that distance that corresponds to where flux would cut off, right? And the thing I like about this is we have a nice empirical constraint from this low redshift system, whose line profiles seem to completely match this galaxy, basically, except for the cutoff. That really have a grip on what the intrinsic profile is. If you use this as a template for the intrinsic profile, that kind of empirically elides a lot of like the issues you would come across if you're trying to do this from first principles. As you say, it'd be like some extra broadening. It could be this that is not necessarily related to the physical scale, but has to do with say, extra collisional excitation and things like that. So that's the basic like comment you can do, like translating that cutoff wave basically into a distance. The more complicated thing you can do is you can do like, which is what Charlotte Mason and Max Branca have tried, is do or like first principles kind of comparison based on like detailed simulations. And what's heartening is that in both cases we find very similar numbers for this object, which has been studied in detail. Those are the two approaches you can take. But the approach basically gives you essentially a lower limit on the size. It could still be larger, basically, the bubble. But it has to be at least that.
Just to get the photons out at all. Sure. Okay. Thank you.
Other questions for Rohan? I'll ask one. This is from some of them, some who just kind of fairly aware of what's happening at those redshifts, but it seemed like at some point people are finding these high shift quasars, and there's kind of a similar question of how do galaxies that form some black holes that massive so early on. So are some of the scenarios that you propose kind of work for both these galaxies you're finding those quasars?
Yeah, that's right. Like buying more time in the early universe to like get an extra defolding. For example, Dan's framework, right? Like growth is going like really quickly at like queer, right? And so just buying time, for example, would very much with that. But no, I do think they're related, but perhaps in some ways, some class of solutions. For example, like the very top heavy IMFs, for example, could fall in the direction of being able to form seeds that are much larger, like typically as you assume. And so, yeah, no, those puzzles are, I think, on some level, indeed quite related. Another thing that we'll do with quasars, which I'm pretty excited about, I've joined this large GTO program studying quasars, is we can do this kind of like age dating. I'll skip over these slides, but the basic idea is that instead of like just searching for like galaxies in these deep fields, looking for very distant objects, you can imagine you're like an archaeologist who's tasked to find like the most ancient civilizations. So instead of digging some random part of this map and like digging deep in the middle of like the Atlantic Ocean, like all the best you might find Atlantis, but you could apply a prior and say that we want to go dig like an ancient river valley civilization where like you're like, oh, the soil was fertile, water was plentiful. So I'm going to like pick, I'm going to go digging in Mesopotamia. And so what you can do is you can start doing this kind of age dating of galaxies, where, for example, we have this JWST program that's scheduled for this coming March, where we have one such river valley-like place, which is really massive over density at Red 9, where about like 1/3 of all dropouts lie in less than 5% of the area that we have surveyed till now. So what do you do there? You can start like doing age dating basically by finding the SECDs of these objects. And so you can do that for the quasar as well very soon in those quasar-like environment. The quasars are still unfortunately at lower rates, at about redshift 7.5, 7 to 7.5. And it's kind of modeling you really want to push to like higher and higher redshifts to like not leave too much room for star formation histories to get diverse. Basically, the highest redshift you can do this is at redshift 9. Yes, they are, but you give them lesser time compared to more. There's lesser diversity. Yes.
Not necessarily.
I mean, the way to think is the way I think about it is you through like quenching, rejuvenation, quenching again, and like form some really complex.
Conservation of matter already gets you that, right? There's different objects are stealing matter from other things, right? You never lose that diversity.
But I guess what I was thinking, right, like shift 6 or 7 galaxy compared to a redshift 9 or 10 galaxy, just because there's lesser time and lesser time for things like AGN feedback, various like chains of like processes, like there's lesser time for that to happen essentially, and so you get star formation that are at least in our binning. Within our binning, simpler and potentially more reflective of what's actually going on. Yeah.
Question from Alan, so can you please unmute and ask? Yeah.
Anna, can you hear me? It's Alan Dressler.
Yes, we hear you.
Yeah, we can hear you.
Okay, sorry. Could you put back the slide that showed the different profiles for the reionization by bright galaxies and fainter ones, and the different profiles?
Like the timeline, or like
no, it was earlier than this. It showed the different speed. Well, maybe this is it. Sorry, this is it. So I guess the question I had is that by the, you said that the bright galaxies match the profile that we observed, which is more rapid than we probably expected. But by the time the bright galaxies kick in, the faint galaxies, if the numbers are right, have already provided half of the reionization. So I didn't quite understand. Are you making the argument that the bright galaxies can do it and that somehow the faint galaxies are not going to contribute, and that's why? Because otherwise, you're not going to get this sharper profile unless the faint galaxies are not contributing.
Yeah, that's exactly right. So in the oligarch model, the faint galaxies do not contribute. You basically have like a peak stellar mass at which things are like most efficient for ionized photon escape to happen. Basically, your ultra-massive galaxies are too dusty, and then lower mass galaxies have just too inefficient star formation to blow holes and push things out of the ISM. So you have galaxies basically in the 10 power 8 to 10 power 10-ish mass range that are doing most of the work. And so your intuition is exactly right. That in the sharp, very late, very rapid model, you do not allow these fainter systems to contribute like in any significant way.
And I didn't catch whether you said you have any observations we know the numbers are probably there. So do we have any observations that tell us that they're not as efficient because of the escape fraction or something else?
No, till now, no, that's exactly what we're hoping in these coming years. Yeah. So till now, it's been very difficult to even get constraints on the escape fraction relatively bright galaxies out to about 0.9 star. But with this method, like using these very resolved alpha profiles, we can push to galaxies that are like 10 to 100 times fainter than the current state of the art, right? Because 11 alpha is so bright. So we currently have 100-hour shooter program, 50-hour shooter program to do an experiment that we did for lensed galaxies that go 100 times fainter. And so we will have an answer about that soon, where we'll have like, basically that 11 alpha profile for these very faint galaxies to make that direct comparison for the first time.
Okay. Can I squeeze in another shorter question? If nobody, I can't tell if anybody else is queued up.
I was just going to ask about the ALMA follow-up. So you mentioned the line for the high redshift candidates, and so for how many of them is it practical to detect the dust continuum if it's an interloper and not at high redshift, or redshift 5 instead of 12 or whatever?
Yeah, for some of them, interloper like should just be extremely bright dust continuum, and so we should have detected like Glassy 13 we did not anything at all. Okay. For Glassy 11 like there's some like hint of something, but then Glassy 11 also has like the largest Lyman break all JWST right greater than 10 candidates at this point, something like half megs, and so even your like super dusty models can't do factor of 10 break. They can do maybe factor of 3 to 5 breaks.
There a question, Ben, or?
Sorry, Alan, I think wanted to.
It was just a shorty. You mentioned that the issue about disks.
Yes.
But in a sense, is it the most surprising thing, the size of these galaxies?
Size is still pretty compact. It's on the order of like 0.5 kiloparsecs in terms of.
So I mean, analogizing these to anything that we would call a disk for a modern day galaxy is kind of a stretch. Maybe this is how do you, and I'm not sure that it really tells you much to say they're disk-like is what I'm saying.
I mean, yeah, not the like thin disk, but the beginnings of the thick disk. Yeah, I think there is something to say there. Yeah.
I mean, they're not thin.
Yeah, I know. Which is why I said not thin disks, but like the beginnings of the thick disk is the idea I was trying to.
Yes, you did say that. Yeah. Okay. Thank you.
Hi, thank you for the talk. I was wondering, maybe you said it already, but when you model the Lyman alpha profile, does your gas move? It has inflows, outflows. Is it stationary?
Yeah, those are all excellent questions. But the point here, I mean, the good thing that we are able to do here, we're able to do this completely emptily at this point. So yes, all locations you mentioned are 100% happening. What we've done now is we've collected enough of a sample of galaxies where we have simultaneous observations in Lyman alpha and Lyman continuum, that we're able to do these kind of indicators kind of empirically to do a really good job separating these very high escape fraction galaxies with very low escape fraction galaxies. So I'm not doing any theoretical modeling at all in these works. I'm just hanging everything empirically for exactly the reason you mentioned, that Lyman alpha radiates from first principles is quite a hairy thing. And to date, we are not able to produce files like these in our theoretical models with like centrally peak, triple peak profiles. So yeah, all this stuff is essentially calibrated empirically based on samples that have simultaneous observations. The calibration is based on yes. So it's a combination of ST stuff for like the slightly higher redshift objects, but the bulk of them are from us at just 0.3 to 0.3-ish. So we have a fairly substantial sample where you don't know the exact number, but you know it's high. for the ST objects, because for any individual line of sight, you do the correction. But then the lower redshift 0.3 sample, that's not an issue, and you can actually believe back numbers.
Anyone else? Okay, if not, let's thank Rohan again.